Next problem now. So again, we've got a beam. So mostly interesting beams for this course. We'll probably chuck in a few examples of some other stuff. But the same thing, says a cantilever beam. It's a load of rubbish. It's not a cantilever beam. So for the beam below, draw a free body diagram and then determine the support reaction. So a cantilever, when it's fixed at one end only, this is supported. This is called a simply supported beam. This one here, simply supported beam. Why? Because it's got, basically it's pins at both ends, but to be accurate, you have to say it's a sliding contact or a rolling contact at one end and a pin at the other end. And that's just because if we had two pinned connection, we'd have four reactions. And we've only got three equations to solve it with, so we wouldn't be able to do it. It's called statically indeterminate in that state, in that situation. That's what it's called. And so you have to put this roller at one end. So you've got 1, 2, 3 reactions. So that's what I'm showing here. So I've already drawn the free diagram. We've got a concentrated moment. That's what this is here. I prefer to draw a dot in the middle. And so that's like your couple moment. It's that sort of thing. So you're just imagining, it's almost as if, I keep saying this, but just to get a picture of what this means, you know, you've got your wheel like so, and you're applying a couple moment to it. So you've got two forces in each direction. That's welded to a point there. And that's really what that means. And the moment on that, so if you take those forces times the lever arm, you should get 500 kilonewton meters. That's what these pure moments, moment couple, couple moment, pure moment, there's all different ways of talking about them, but that's what they are. You're just sticking a wheel on there, welding the shaft of that wheel to this, or this is more like a handle, and welding the shaft of that to this object, and you're twisting it. And just remember that what we talked about before, it's called a free vector. The reason it's called a free vector moment is because you can move this anywhere and it won't change the moment reactions. So, or sorry, it won't change the external reaction forces. So it won't change these forces no matter where it is. So these are always quite easy when they're in a question. You just add them to the moment at the end. You don't have to worry about cancelling them out or anything. You always apply those. So let me just get rid of that. So just keep on thinking about that. I know I'm maybe labouring this. I'm just nervous that maybe this is a possible point of confusion. So you can get one moment that comes from a force like that. So you've got some point, you're applying a force to the end of a handle or something like that, and you measure the moment about that force, and the moment is just F times D. Or you can get something like where you've got a point and you apply, maybe you've got two handles or you've got a wheel or something like that, and you're applying one force this way, one force that way. Okay, they're equal and opposite and parallel and separated by a lever arm, and the lever arm that you take is just this distance here. So that's that distance D, and then maybe these are F, so let's say that's F and that's F. The moment for that is also F times D, and in one of the other videos I showed you why it's not 2F times D, you know, it's just F times D. This is called a couple, and the way you represent that in diagrams is to draw a point with that and then say the value. So F times D, so that might be like 20 kilonewtons or something like that. 20 kilonewton meters. 20 kilonewtons is a force. You need that force times distance, or force times lever arm. So you might write beside it 20 kilonewton meters. And you could get that in lots of different ways. So if you were thinking of the actual forces you'd be applying, it's got to go that way so that it's got the right rotation, so it's clockwise, so that would be a negative. This is the magnitude. I've shown the direction here, but if you wanted to try and express the direction just in terms of a number, you'd write that as negative 20 kilonewton meters. But if it's a couple, why was I saying that? Oh, because there's lots of different ways you could draw that. So you could do 10 kilonewtons, 10 kilonewtons, and they're separated by 2 meters. Then the force times distance would be 20 kilonewton meters, or you could do 5 kilonewtons, just got to make sure you get the right, but you could separate them by, have a lever arm of 4 meters, you'd still get this, and that's why we tend to draw it like this, so that we don't have to, you know, it could stand for any one of these. It just means that you're grabbing that little point there and you're twisting it with this moment by applying a couple, so that the other interesting thing about these is the forces cancel out, so it's got no force associated with it, or no net force associated with it, and that's why it's called a pure moment. Okay, so labouring that a little bit, but it's important that you get your head around that. If it's still not clear, go and find a textbook to read or look online what's the difference between a moment and a couple. See if you can find someone who can explain it better than me, which is probably just about everyone. Rightio. Oh, and there's also Terry Bennett stuff. Have a look at Terry Bennett stuff. He'll probably explain it as well. So where were we? So I've drawn my free body diagram. I've drawn on this pure moment. I've drawn on already. Drawn on my reaction. So it's a pin. So it's got a y and an x. But I'm already looking ahead, and I've got no x applied forces. There are no components applied in the x direction. Why did that come back? It's not a cantilever beam. It's just a beam. So therefore, this is just going to disappear. So Rex is going to be 0 because we don't have anything else causing an x component of force in this. And the sum of the x components must be equal to 0, so that must be 0. What I haven't drawn yet is I haven't drawn the distributed force, so this line load. Okay, so we've got a line load here, we've got one triangle here, so let's just draw that on. And what are we doing here? We've got a moment, I might call that M1. So this might be M1, or it could be just call that M1, I reckon. So then we're going back to what we learned about line loads and how to find, what we're going to do is we're going to represent these by a point load rather than trying to figure out this line load. We're going to represent them by a point load. So you're finding the equivalent point load for this. And so you're going to end up with just a point load. So the line load will disappear. We'll get a point load. And remember, it's 1/3 of the way along from the right angle, or it's 1/3 of the way along the height of the triangle if you were to rotate this by 90 degrees. So you're going 1/3. That doesn't really look like 1/3. It's probably somewhere here-ish. Right, so it's going to be 7.5 take away 1/3 of 7.5, or you could say it's going to be 2/3 of 7.5 along from there. So we'll probably call that F1. I might not want to do that. Let's call this, so what have we got here? I'm just thinking if I get a moment from this, that should be okay. I just don't want to end up with two M1s. So if we're calling this M1, so let's just give this a proper name. It's at 0, even though it doesn't matter where you apply it. We'll call that M0, just so I don't end up with two M1s somehow. We've got an F1 here, and we have got another F1. Let's just put that, another force for this UDL. So you just figure out we've got to figure out the magnitude and position of that force. The magnitude is the area under the triangle. The position is just using the rules. You just look back at the rules that we gave you, and it's going to be 1/3 of the way along that side from the right angle. And so it's going to be 7.5 plus 4.5. Okay, so what I'll do now is I'll just go through the calcs for figuring out those two forces. The important thing to remember here is that force, it won't change these external reactions. So by changing this UDL to a force, you don't change the external reactions. But when we get to stuff about internal forces in this beam, you cannot do this. You can't turn it into a force. Because you just imagine if instead of that UDL, you're implying a force here. Well, for this point here, in the middle of this beam, something for this point here, something has changed for this point. It used to have some of this line load going to it. Now it doesn't have anything except this point load. So the internal forces will change. We'll understand that a bit more once we do some internal forces. But by finding an equivalent force for that line load, I think I called it a UDL. It's not really, it's a line load. UDL is flat. For that line load, if you find an equivalent point load, it won't change the external reactions. That's the thing to remember, but it will change the internal forces, which we're covering next. Okay, so I'll just find those two forces and I'll draw them on my free body diagram, and then we'll take it from there. Okay, so I've now found those equivalent forces for those UDLs. So now we've simplified it to a problem where it's just point loads. It's all point loads. Like I say, you can do that if you're finding external reactions. You can't do that if you're finding internal forces. I think we've done everything. So now we just work through this in the same way. Just thinking ahead to think what's the easiest way to do that. Well, first I can eliminate Rex because I've got no x component of force anywhere. So the sum of the Fx is going to mean that's 0, so that'll be that done. And after that, it doesn't really matter which of these I choose. If I choose this side, I'll get, the next thing I'll do, I could do the sum of the y components must be equal to 0, but I'll get two variables for that, but that's okay. Get two variables for that. I won't be able to solve that just yet. But then I can use one of these points and find the moment about that point, because that'll eliminate one of the forces. That'll mean I can get the other force. This is always included no matter where it is, so that doesn't need a lever arm because it is a pure moment. And so even though that's here, you'll still have to allow for that when we're using this point. So what will I choose? So I think I'll just write out the different equations. So let's just start. I wonder if I'll just fast forward through this. I think I will. I'll fast forward through this and I'll come back to when I get to something that I think you might be interested in. So now I'm just looking at the sum of the moments about this point 0. I've decided to take for no particular reason, no matter which one. So we still have to count that. Now I've ended up with 2m naught. Oh, well, no, that's not right. It's the sum of the, well, I do have to write that. So let me just change that. So m naught, I'll just call this one m1, because I don't think I'm going to use a f1 anywhere. I'll just, if I have to write out the moment due to this, I'll just do f1 times d1, if you know what I mean. So we'll call that m1. So the sum of the moments, because it'll get confusing, because the sum of the moments about 0 must be equal to 0. So that must be equal to 0. So that implies, what does it imply? So it means now this m1 is going in a clockwise direction, thumbs down. That means it must be negative when you're putting it into this equation, so minus 500. Then I'm going to figure out this one here. So we've got 22.5, and it's also going, it's trying to move it in a clockwise direction, 22.5 times 5. So that's also minus 22.5 times 5. And this one's the same direction, so it must be minus 13.5 times 9. Then the only one that's going to counteract all this is this RAY. So it must be plus, because it's going anti-clockwise about the point O. So RAY times 12, I think, is the total length. 5 plus 4, 9 plus 3, 12. Must all be equal to 0. That means 12 RAY, take all these negatives to the other side, they'll become positive, and we'll just add those up. It'll be 500 plus 22.5 times 5 plus 13.5 times 9, 734. Oops, sliding away, 734. So therefore RAY must be equal to 734 divided by 12, which is equal to 61.2. 61.2 what? Kilonewtons. Pretty big. So it's pretty big compared to these forces. Why is it so big? Because this is quite a massive moment that's on this. So this moment is trying to swing this whole thing down. Then you've got these trying to swing it down the way. This one's trying to swing it down the way. So this has to be quite a big force to support all those moments. It's got a decent lever arm, so it's a lot smaller than the 500 kilonewton meters. The force is only 61 kilonewtons, but it's a big, probably be a big force compared to this one. But let's have a look at that. Could even end up being negative, this one. So let's have a look. Could be interesting. So I've drawn that on as it's positive. If this magnitude comes out as negative, I'll know that this is in the wrong direction. So let's have a go at that. So, what was I doing here? Yeah, it definitely is. So now we can take this, so let me just give it a name. So let's call that 1. We're going to substitute that back into 2. So sub 1 in 2. And so we're going to get ROY plus 60, definitely is positive, it is, because it's going upwards, plus 61.2 is equal to 36. Therefore, ROY is 36 minus 61.2. Well, I should be able to do that in my head, but I'm getting old and foolish. So 36 minus 61.2 is minus 25.2 kilonewtons. So we've ended up, so we've drawn it here this way. We've used that direction to calculate the moment, and we're ending up with something negative. What does that tell me? Tells me it's the other way round. So what you can do, or what I guess I would do to keep it tidy, is I would just draw the, gets a bit confusing. I draw that the other way round. So ROY, and then I might even go through, does that get confusing? I think it does. We better just leave it like that, because I'm thinking that's going to stuff up this stuff. I'd now have to put negative ROY in there. I could do that. So I could change the direction of that, put negatives in here, work it through, I'll get something positive. But that means that, what it means is, is that ROY, I showed it as going up the way. I've got a negative magnitude here, so it must be that value, and it must be going down the way. Okay, it's a reaction down the way. And the more I do these questions, I'm thinking it's better just to show it with an arrow rather than do your positives and negatives. It can get too confusing. So just show it with the arrow. Okie dokie. So have we answered everything? I think we have. So reactions are, well, let's say as per above sketch. ROY is equal to 25.2 kilonewtons down the way. RAY is equal to 61.2 kilonewtons up the way. And RAX is equal to 0 kilonewtons, or just 0 kilonewtons, because there were no X components in the other forces. And that's us done, but we'd be a bit daft to leave it there. What we do is we've calculated all the moments about this point here, this point 0 or 0 or origin or whatever it is, O. What we'll do now is we'll just calculate the moments again around this point A, just as a check. So let me take this down so that I can see it. And we'll turn it grey because we're just checking. So I'll run through that check and I'll see you on the other side. So again, I almost made a mistake there because I didn't change this ROY. You know, I was showing this upwards. And so I put this ROY, you know, if it was this one here, that would be a negative moment. But in fact, it ended up being downwards. So I just redrew that from a check. So ROY is going down the way. And so then I've worked through that and figured out that I've got the sum of the moments about A is 0.4 kilonewtons. So we can be pretty sure we've got the right answer because that's within the rounding error. So here, for example, I've got a 22.5. So we've got it correct to 1 decimal place. Sometimes in that there's 7. So to be out by 4 decimal, what am I trying to say? To be out by 0.4 is well within the rounding error. So I'm happy to accept that I'm pretty likely to have got the right answer. Okay, I think I've got one more example just to show you something that's a little bit tricky. That's not a beam. And that one you'll kind of see how I stuff up and try and fix it. Can't figure out what to do and then figure out what to do. And I decided to stick that in anyway, just to show you that it's often you can take time to find the right way to get the right answer. You've got to try lots of different stuff first. Done. Bye.